So we briefly discussed the equations that show us the eddy momentum and heat fluxes and how the tilted structures are needed for net poleward transport. What do the observations say? So this is a nice figure that is showing pole-to-pole latitude height sections of the observed zonally averaged total northward eddy heat transports for DJF and JJA as usual. And we are showing here the 500 hectopascal vertical velocity as well in this red line. You can again see the seasonal contrast. Basically during winter you have a stronger equator to pole temperature gradient in the winter hemisphere, which means you need more poleward energy transport from the tropics, which means you're going to have stronger eddy transport in the winter hemisphere, which is clearly seen here, which happens to be just north of the that's the maximum. The bold red curve shows the 200 hectopascal zonally averaged zonal velocity component. It's not the vertical, it's the zonal, obviously. Boom. Okay, so you can see that the maximum eddy transport is just to the north of the maximum here in the winter hemisphere, whereas here it's equatorward, and the zonal maximum westerly, of course, is weaker in the summer hemisphere, and the situation switches when we have the seasonal change. So now you have summer hemisphere, weaker eddy transport here, stronger eddy transport here, but you can also see the seasonal hemispheric uncertainty. This winter eddy transport is stronger than this winter eddy transport because of the asymmetries in the land distribution, ocean distribution, Southern Ocean role in this whole process, and the ITCZ itself being mostly located in the northern hemisphere. And remember that the ITCZ is the energy equator because the ocean is moving energy northward, and so on. So all those details are in here, but the observed eddy transports obviously are computed by taking the flow field, full flow field from something like the ERA interim reanalysis data, which, in case you don't know, is a blending of all the available observations with a dynamical model so that it can reconstruct the past history of climate and look at 3D processes that are not captured in the data alone. And just running the model is going to probably produce some biases, but assimilating or blending the data provides a dynamical constraint as well. That's typically how reanalysis are justified, even though they themselves have all kinds of problems. So that's the momentum flux here. Look at the eddy heat flux. Obviously the same story. You have a strong poleward eddy heat flux in the winter hemisphere, almost disappears in the summer months because there is not much of a transport happening by this process. And you can see again the asymmetry in terms of much stronger northward winter eddy heat flux here compared to the southward winter eddy flux here. Okay, so that asymmetry remains. So that gives us a good idea that the region where, of course, we have convergence in the low latitudes here, and the ITCZ moves with seasons, as we remember. So the convergence and rising motion is in these latitudes, and then there is sinking motion and the termination of the Hadley cell here, and the entire Hadley cell itself moves back and forth with the season. So you can see that the eddy transport itself also moves. The westerly jet moves, so you can see that this is centered around 60 north, this is centered more around 50 north or southward, and similarly there is a shift here, 60 north in the summer months and around 60 south and 40 south, and so on. So all kinds of dynamic details are there in these simple pictures. Looking at the eddies and the mean circulation, we should then remember that Charney and Eddy, then many studies that followed, showed that the basic state of the atmosphere set up by the latitudinal radiational heating gradient is unstable. Eddies were the product of instability and returned the system to equilibrium. So there are many ways to say it. These thermal winds, vertical shear, strong westerly jets, zonal westerly jets become unstable, and we'll see later on that if you lift air parcel in the tropics and carry the angular momentum of the low latitudes, which is high because the radius is high, zonal velocity is high. As you move northward, angular momentum cannot be conserved, as we will see, because the radius decreases and the tangential velocity needed to maintain angular momentum gets unrealistically large. So you end up getting hydrodynamic baroclinic instabilities, which is what produces these eddies. And when you have deviations from the zonal symmetry, there are other processes that bring the system back to equilibrium, and we'll see how that works. Okay, so it's interesting to note that the instability is induced by the radiative imbalance between the low and high latitudes, and is an example of a perpetual instability because the sun is always moving back and forth, that varies slowly with season as the radiative balance changes. So the way this book is written, the Hadley cell is being discussed, tropical extratropical interactions, tropical influence on the extratropics through these eddy fluxes of momentum and heat, but without saying anything about the termination of the Hadley cell. How far does the Hadley cell go and what determines where it stops? It's just implied here that these baroclinic instabilities are what determine the end of the Hadley cell, but it's not the only theory that exists, as we will see. Okay, so I'll come back to these equations in the next podcast, but you get the idea. Observed eddy fluxes clearly show that there are peaks in the winter hemisphere at the termination of the Hadley cell where the westerly jet streams are, and there is clear poleward transport of eddy momentum and eddy heat fluxes, and they are done with these tilted structures that we saw in the satellite data animation as well as in a schematic. Okay.